Hello everyone, we're going to start chapter 3. The first topic in chapter 3a is finding the atomic mass from isotope mass and natural abundance. We learned about isotopes previously. You'll recall for an isotope, it's the same number of protons, but a different number of neutrons. Recall that protons are the identifying component of the atom. So for an element to be an isotope, it's going to have the same number of protons always, because that's the identifying factor of the element. But if an element has different isotopes, then within those isotopes, it's going to have a different number of neutrons. With a different number of neutrons, but the same number of protons, that leads to a different atomic mass. For example, carbon-13 and carbon-14, these are isotopes. They have a different atomic mass, 13 versus 14. But the atomic number for carbon is 6, meaning that carbon, any isotope of carbon will always have 6 protons. So 6 protons, that will never change. So keep in mind this definition of an isotope. So in this practice problem, we're going to use this table of data to fill in these blanks here. And just another reminder here, remember there are more practice problems in the main slide deck. So if you want more practice to look at, go ahead and refer back to that main slide deck, and or let me know in office hours if you want to work through any additional practice problems. As was just mentioned, the answer is that the atomic number defines the element. So for this element here in our practice problem, we have the element symbol Mo, that's molybdenum. Molybdenum as an element will always have atoms with 42 protons. How do we know that? We can go to the periodic table, find molybdenum that has 42 as its atomic number, therefore it has 42 protons, always. Every isotope of molybdenum will have 42 protons. By contrast, however, the exact value of the atomic mass will depend on the number of protons and the number of neutrons. And so we know for isotopes, it's elements that have different numbers of neutrons from one another. So what we can tell by looking at these symbols here is that this atomic mass is 96, this atomic mass is 98. So now if these are the two different isotopes of molybdenum, then when we see the reported atomic mass on the periodic table, so atomic number will be here. I should have pointed here. So when the reported atomic mass, this reported atomic mass is the average atomic mass. That means that we're taking into account all the different isotopes and their individual atomic masses, and then we're looking at how much is present of each to get the average atomic mass for all isotopes of molybdenum. So on the periodic table, when you see that average atomic mass, it's reflecting the relative abundance of all the isotopes that exist for that element. Depending on the specific element, sometimes the relative abundance might be 47 and 53%, for example. Alternatively, for some elements, one type of isotope can be up to 99% of what makes up all of the atoms that exist for that specific element. So one isotope might be 99% relative abundance, while another more rare isotope might only be 1% of all the atoms of that element that are present. So relative abundance will just depend on the specific element. It can be about half and half for two different isotopes. It can be up to 99% for one isotope, while only 1% for the other isotope of that element. So again, the relative amounts of the different isotopes will end up telling us the element's average atomic mass. So it's average atomic mass. So we've defined this now, this average atomic mass. Let's talk a little bit more about it. It's the weighted average of all the naturally occurring isotopes of that element. So naturally occurring means that they are found in nature. We can actually make some isotopes in the lab, but the average atomic mass on the periodic table will reflect the weighted average of all the naturally occurring isotopes. Again, recall that isotopes are the same elements, the same number of protons, but a different number of neutrons. Because of that, then, isotopes will differ in their atomic mass. For example, when we look at the periodic table, we'll find carbon with its atomic number of 6. That is the number of protons. However, when we look at the atomic mass, 12.01, that means that we have some additional isotope here that's not just with an atomic mass of 12. So a lot of the naturally occurring carbon will have an atomic mass of 12 because this average atomic mass is so close to 12. But there must be something else present that's adding to that average atomic mass. So I mentioned that isotopes can exist in about half and half, or they can also exist here. So carbon-12 is the much more commonly found isotope of carbon. In fact, all naturally occurring carbon, 98.90% of it is carbon-12. What does that mean? It means that this percentage of it has an atomic mass of 12. So because we know we're working with carbon, that means it's going to have 6 protons always. And then from this atomic mass, it will have 6 neutrons. So this isotope has 6 protons, 6 neutrons. Now for this isotope, carbon-13, it's still going to have 6 protons because it's carbon, but then 13 minus 6, that means it's going to have 7 neutrons. So this isotope has 6 protons and 6 neutrons, making its atomic mass of 13. But this isotope is only present as about 1.1% of all carbon that's naturally occurring. So with these two isotopes that can exist naturally for carbon, that's where we end up using this weighted average. So 99%, about 99% weighs 12 atomic mass units, while about 1% of all carbon that's naturally occurring weighs 13 atomic mass units. So with that combination, if we were to do that weighted average calculation, that's how we get this reported average atomic mass on the periodic table. It's not exactly 12 because about 1% of carbon that's naturally occurring, it does not just weigh 12 atomic mass units, it weighs 13. So that's where we get this value that's not exactly 12. So what we see on the periodic table is an atomic number, an atomic mass, the average atomic mass. For the atomic number, we know now, even for isotopes of sodium, they will always have 11 protons. It was hard to see exactly in that last image, but sodium has an average atomic mass reported at 22.990. So that would mean that a fairly large portion of all the sodium that exists naturally has an atomic mass of about 23. But then there's also definitely some isotope that has a smaller atomic mass, which is causing this average to be a little bit less than 23. So for 23 atomic mass units, the average atomic mass of sodium, we know the number of protons is 11. So 23 minus 11, that would mean that the dominant version, the dominant isotope of sodium, has 12 neutrons then. Something else I want to point out here, so if there is an average atomic mass on the periodic table that's not quite a whole number, the way we would end up treating this is going ahead and rounding this to a whole number to say this is 23 AMU. We need to round this up in order to actually determine the number of neutrons because we're not going to have a 0.9 of a neutron. So we rounded that up to get this number of neutrons and protons into whole numbers. Generally, we report the number of protons, neutrons, and electrons as whole numbers. Okay, so this holds for any average atomic mass for any element that you see on the periodic table. So the atomic mass of an element, like the one in our practice problem, is defined to be the average mass of the atoms in a typical pure sample of that element. Importantly, the atoms do not usually all have the same mass, because usually a sample will contain several different isotopes of that element. So really what these practice problems get at, and this idea of the average atomic mass, is being able to use the formula for a weighted mean or a weighted average. You may have used a formula for a weighted mean or a weighted average in trying to calculate your grade at the end of the semester, trying to calculate your GPA, different things like that. So we're going to cover how to use this idea of a weighted mean in chemistry, so for elements and their average atomic mass. Let's talk through this first example here. So for atoms of element X, if there's a 50-50 mixture of this isotope X95 and this isotope X97, then if half of the atoms of element X weigh 95 atomic mass units and the other half weigh 97 atomic mass units, then the average reported atomic mass of element X is going to be the average. So we would say 95 plus 97 divided by 2, the total number of values that are being inputted into this average. This was the case if these are in a 50-50 composition for element X. We did not have to use a weighted mean because these are both weighted the same. Right, this is half of the atomic mass, this is the other half. But this is not usually the case where isotopes are exactly 50-50. Instead, for example, let's say that 47% exists for this isotope, 53% for this isotope. That means that we can't treat these evenly because this is not 50% and this is not 50%. This is weighted a little bit less than 50% and here a little bit more than 50%. So here's the overall gist of these steps. Notice that here is the percentage of one of the isotopes. Here's the mass of another isotope. Here's the percentage of the second isotope, the mass of the second. You could apply this formula to 3 different isotopes, 4 different isotopes, etc. And from PEMDAS, we know we're going to multiply first and then add. Here again is just the gist of the steps. Let's talk through each one individually. So notice here, here's mass 1, here's percentage 1, mass 2, percentage 2. The step from here to here is extremely important because notice that we do not work with this value as a percentage. You must first take the percentage into a decimal form by dividing that percentage by 100. So 47% divided by 100 gets us into the decimal form of that value of 0.47. 53% divided by 100 gets us into this decimal form of the value of 0.53. That step is extremely important. You have to get these percentages first out of a percentage. Then we'd end up multiplying here, then we add those two together. Along the way, you should keep the number of sig figs until you get to the end, and then for your final answer, go back and decide how many sig figs we should have in our final answer. To determine the number of sig figs in our final answer, we had these values originally, so 47% and 53%. Technically, there are no digits past the decimal place here. So for our final answer, we should also have then no digits past the decimal place. So although we end up getting this answer here, we need to round that to only have 0 digits past the decimal place. So this part up here is extremely important, being really comfortable going from a percentage to a decimal form of that value. And keep straight that this 47% corresponds to the isotope with 95.9 AMU for its atomic mass, where 53% is for this isotope. So you should be able to carry this formula on for, again, 3, 4, 5 different isotopes of the same element. To get more practice with this, I want to encourage you again to go to the main slide deck. and look at those practice problems. There's some with coins. There's more of these isotope practice problems. So definitely work on a few more and get even more comfortable with this concept of average atomic mass and using a weighted mean or weighted average formula. So here we determine the average atomic mass is 97 AMU. Remember, AMU stands for atomic mass units. I also told you that we'd eventually know that 1 AMU is the equivalent of a gram per mole. And so we're going to talk more about that today. So for molybdenum, it's always going to have the same number of protons or the same atomic number. So that's 42. Here then is the average atomic mass. This is the number of protons and the number of neutrons. We can think of this as AMU and grams per mole. This number is a little bit different from what is actually on the periodic table for molybdenum because this is a hypothetical scenario. So we just went through how to do that problem, but this 97 for molybdenum is not what you'll see on the actual periodic table. So just a heads up for that. All right, if you have taken a sort of chemistry before in high school or previously, you've heard of Avogadro's number. Avogadro's number is 6.022 times 10 to the 23rd. When we correlate the average atomic mass for a specific element, and I was telling you this is the same thing as grams per mole, Avogadro's number correlates with this idea of the mole. Notoriously, the mole can be a little bit difficult of a topic to really wrap our heads around, so let's go through it. The mole, or abbreviated like this, MOL, is a unit to count the numbers of particles. So it's a way to count the numbers of particles, where particles can be how many atoms are present in a sample, how many individual molecules, how many individual ions. So number of particles, you may also hear called the number of elementary entities. For example, for the number of ions, we could ask something like how many elementary entities are in a sample of sodium cations. The elementary entity would be the number of ions there. So how many ions are present in a sample of sodium plus ions? You can imagine it'd be pretty difficult to figure out exactly how many individual atoms are present. So we'll talk about how to do that using Avogadro's number. What about for molecules? How many elementary entities are present in a sample of water? The elementary entity then for water, we could be wondering then the number of molecules of water in a sample of water. So it's a way to count the number of elementary entities, be it the number of atoms, molecules, ions. We'll go through a few different examples with these calculations. Where did we get this huge number from? It's actually the number of atoms in 12 grams of carbon-12. Remember carbon-12 then, because it's carbon, we'll always have 6 protons. From this atomic mass, 12 minus 6, it also then has 6 neutrons. So Avogadro was able to determine the number of atoms in exactly 12 grams of carbon-12. This determination led us to this value here. So 1 mole, represented as Avogadro's number, or N sub A, is 6.022 times 10 to the 23rd. Some analogies that may be helpful to think about. So why do we need this concept of a mole? What is it really telling us? Well, instead of saying we have 12 eggs, it's become commonplace to say we have a dozen eggs. This dozen is just a way to describe 12 eggs. So 1 mole is just a way to describe 6.022 times 10 to the 23rd, elementary entities in some sample, or 6.022 times 10 to the 23rd, ions or atoms or molecules in some sample. Instead of saying 12 eggs every time, we just say 1 dozen. Instead of saying this number of atoms or ions or molecules each time, we just say 1 mole. 2 shoes, we usually don't say, hi, I'm here to purchase 2 shoes. We would say, hi, I'm here to purchase a pair of shoes. This pair is automatically connected in our heads with it being that number of 2 shoes. So think of this pair, 2 shoes. When you hear the word mole, we know there's this long number here. Instead of using this long number each time, instead of saying this long number each time, we refer to this as a mole. When we do calculations, we will use this Avogadro's number in calculations related to the mole. We'll get to some examples soon. So let me connect something to you for the mole and then what we see on the periodic table. I keep saying that 12 atomic mass units that we see, that's really the same as 12 grams per mole. So 1 mole of carbon-12 atoms, 12 grams of carbon-12 atoms is really this number of atoms, or Avogadro's number. Well, on the periodic table, 1 carbon-12 atom, we can see that its atomic mass, its average atomic mass, is 12 AMU, or 12.01 AMU, depending on which version of a periodic table you look at. So 1 carbon-12 atom weighs 12 atomic mass units. We're still trying to connect atomic mass units to Avogadro's number, so let's keep going. If 1 mole of carbon-12 atoms weighs 12 grams, and 1 carbon-12 atom also weighs 12 atomic mass units, then 1 mole of carbon-12 atoms weighs this many grams. This becomes extremely important now because anytime we look at the periodic table, we can say that carbon weighs 12.00 grams per 1 mole. Another way you'll see this is 12 grams per mole. So when you look at the periodic table, this average atomic mass, just go ahead and correlate that with atomic mass units and the number of grams per mole. If this is all based on carbon, then what about all the other elements, you may be wondering? Well, this initial determination of 1 mole of carbon-12 atoms, 12 grams of that being this number, Avogadro's number, that's the baseline for all the other elements. So we can apply this same reasoning for every other element on the periodic table. For example, what about hydrogen? Well, hydrogen must weigh 1.008 grams per mole. Zinc, 65.38 grams per mole. Here's carbon that we've talked about. Oxygen, 15.999 grams per mole. Okay, so this holds true for every single element on the periodic table. So get very comfortable thinking of this average atomic mass as AMU and units of grams per mole. This concept that we've been talking about so much is the molar mass. The molar mass is the mass in grams of 1 mole of any item. In other words, molar mass is the number of grams in any 1 mole of any item. If we had 1 mole of eggs, for example, if we took 1 mole of eggs, we put that all together and we weighed 1 mole of eggs, we would get that weight in grams. The weight in grams of 1 mole of those eggs is its molar mass, the molar mass of eggs. Of course, we don't usually do that with eggs, but this is just an example. So hopefully this is connecting more and you're getting the important takeaways here. One being that molar mass is the mass of 1 mole of any item reported in grams. We think of molar mass in units of grams per mole. Okay, let's continue to move on here. Lithium is another example we could look at. 6.97 is here, or depending on what version of the periodic table we look at, 6.941. If we see that on the periodic table, or 6.941, that means that 6.941 grams of lithium is how much 1 mole of lithium atoms weighs. Why are we talking about atoms here? It's because we're dealing with lithium, and lithium is an atom. Or I should say, lithium is an element composed of atoms. We can apply atoms to molecules, to ions, as mentioned earlier when I was first introducing the mole. For example, we'll talk about how to calculate this when we don't just have a single atom present. Let's say we have water where there's 2 atoms of hydrogen, 1 atom of oxygen. I'll show you how to get this. This is 18 grams. That means that 1 mole of water molecules weighs 18 grams. We'll come back to more practice on this, but just as I was talking about water here, hydrogen, there's 2 of them. They weigh 1.008 grams per mole. Oxygen, 15.99, or rounded up to 16 grams per mole. For the molecular mass, or the molar mass of water, then we have 2 times about 1 plus the mass of oxygen is 16. This leads to water having a molecular mass or molar mass of 18 grams per mole, or 18 AMU. So we can apply this to single atoms as well as molecules or compounds composed of more than 1 type of atom. We'll do a lot more practice on this as well. Okay, so that's how we got this here, that 1 mole of water molecules weighs 18 grams. Oxygen weighs 16, each hydrogen weighs about 1, hence 18 grams total for 1 mole of water. I'm jumping a little bit ahead of myself here, but we will come back to dealing with more than just a single kind of atom, like lithium or carbon, for example. So this is a nice way to imagine this as well. So if this molar mass being the weight of 1 mole of any item, the weight in grams, this is carbon here. If you're thinking it looks like charcoal, it's because charcoal is essentially powdered carbon. So 1 mole of carbon weighs 12.01 grams, like we saw previously. So 12.01 grams of carbon is 1 mole of carbon, hence how we get the molar mass in grams per mole. This is sulfur. So 1 mole of sulfur has a mass of 32.07 grams. So 32.07 grams of sulfur is 1 mole of sulfur. So for sulfur, we would write it as 32.07 grams per mole. We can also figure out how much 1 mole of these nails weigh. That may be a certain metal. We can also figure out how much this wire weighs. If it's copper wire, for example, we could go to the periodic table, find the grams per mole of copper, meaning that 1 mole of copper will weigh a certain amount of grams. So this sample must weigh that number of grams, making this 1 mole of copper. How many grams do you think this is? Well, this is 12 grams to make 1 mole of carbon. This is going to be 32 grams to make 1 mole of sulfur. For copper wire then, how many grams is this if we're told this is exactly 1 mole of copper? Well, here's copper. That must mean that 1 mole weighs 63.546 grams. So 63.546 grams per mole. So this must be about 63 grams of copper. It's also 1 mole of copper. So 1 mole of these items is going to look a little bit different, right? This needs to be 12 grams, but for sulfur, we need 32 grams to have 1 mole. For copper, we need to weigh out 63 grams for this to be 1 mole. Okay, so hopefully this is kind of interesting to look at a visual representation and comparison of these different substances and how we can see that they're each 1 mole. With all of that background, let's try to apply what we've learned to this practice problem. An aluminum atom has this certain mass, and a small airplane has this mass. From this information, we're going to get the mass of 1 mole of aluminum atoms. We're going to get how many moles of aluminum atoms have a mass equal to the mass of a small airplane. For this information here, more background, we've talked through a lot of this. A mole of X is the same number of X as there are carbon atoms in exactly 12 grams of carbon-12. Where a carbon atom is very, very small, so there are a lot of carbon atoms in 12 grams of carbon-12. How many atoms are in 12 grams of carbon-12? Well, the exact number of carbon-12 atoms in 12 grams of carbon-12 is Avogadro's number, or 6.022 times 10 to the 23rd atoms. Remember, Avogadro's number can also be represented as N sub A. And although we are working with carbon here, this does correlate to other elements in the periodic table. So a mole of carbon dioxide, so a molecule now. So a mole of carbon dioxide molecules is N sub A carbon dioxide molecules. So reading this, it is easier to write it out, I think, to visualize it. So what this is saying is 1 mole of carbon dioxide molecules is equal to 6.022 times 10 to the 23rd carbon dioxide molecules. 1 mole of CO2 is this many molecules of CO2. Remember, we can apply this to atoms, molecules, compounds, eggs, shoes, whatever else we want to apply it to. So 1 mole of cabbages is equal to 6.022 times 10 to the 23rd cabbages. I'm jumping ahead to this slide. We'll come back to it. Here are some examples of how else we can use Avogadro's number. So atoms to moles, particles to moles, cabbages to moles if you'd like, molecules to moles, ions to moles. Eggs to moles is another one. Notice that 6.022 times 10 to the 23rd is always here, and it describes one of these sort of elementary entities or units, and then 1 mole is on the other side of this fraction. So think of it as 6.022 times 10 to the 23rd somethings per mole. So here in this practice problem, let's first calculate the mass of 1 mole of aluminum atoms. The mass of 1 mole of aluminum atoms is going to be the molar mass of aluminum atoms. Remember, molar mass we always think of as grams per mole for the units. In this practice problem, we're told an aluminum atom has a mass of this many grams. So far we can write out that 4.48 times 10 to the negative 23rd grams is 1 aluminum atom. The next part of the conversion that we need is Avogadro's number. So 6.022 times 10 to the 23rd atoms in 1 mole of anything, right? It can be particles in 1 mole, it can be cabbages in 1 mole. Here's 6.022 times 10 to the 23rd atoms in 1 mole of aluminum. So when we do this calculation, we're going to take 4.48 times 10 to the negative 23rd times 6.022 times 10 to the positive 23rd. Be sure to use parentheses here in calculations like this, especially keeping this whole value together. When we do this math, we get this value here. So 26.979, the units are interesting now. So here in Alex is just listed as grams, but we have to think about what we just did, right? We're calculating the mass of 1 mole. So this is really grams per 1 mole. So this is basically saying that 1 mole weighs this many grams. We're also saying the same thing, but we're showing it in a slightly different way. so 26.979 grams in 1 mole. Here we also know just how, from the question is worded, that this is 1 mole. So this many grams in 1 mole, also written like this. So that was for aluminum. Then the second part of the question, we're asked how many moles of aluminum atoms have a mass that's equal to the mass of a small airplane. So how many moles of aluminum atoms have a mass equal to 5,000 kilograms? Well, each mole weighs 26.979 grams. So we need to take 5,000 kilograms divided by 26.979 grams to tell us how many moles then of aluminum. We need to watch out for the units here, kilograms and grams. We need to change one of them first. So for this unit conversion, that should look familiar from chapter 1, 5,000 kilograms. To get this into grams, 1,000 grams is 1 kilogram. So 5,000 times 1,000 will end up being a very large number with 1, 2, 3, 4, 5, 6 zeros after it. Another way to write this then is 5.000 times 10 to the 6th. So the small airplane weighs this many grams. We have this knowledge here of aluminum, that each mole of aluminum weighs 26.979 grams. Now, because we're in the same units, we can divide 26.979 grams to then give us how many moles. When we do this division, be sure to do this part first, then divide. We'll get 1.85 times 10 to the 5th moles. The key part here in this kind of practice problem is to be able to figure out this grams per mole. How else could we have known that's the molar mass of aluminum? We could have gone to the periodic table to see 26.982. When you see that number for aluminum's atomic mass, remember we think of this then as grams per mole. 1 mole of aluminum atoms weighs 26.982 grams. This kind of problem also encourages you though to think about this definition and how we use Avogadro's number. So we had the gram amount, then to get this into a per mole basis, we needed to use Avogadro's number. One thing that is important to point out at this point is that we can count huge numbers of tiny things by weighing them, right? If we know how many grams there are, and we use the periodic table to give us information about grams per mole, then we can also get a value into a number of moles. So here, that's what this is saying. You can just weigh out how much you want, divide by the molar mass. Molar mass is grams per mole, to find the numbers of moles that you have. So to go from a mass in grams to figuring out a number of moles, we can use the molar mass that's in units of grams per mole. This is going to be really important as we continue on for the rest of the semester. So after watching this, after doing more practice problems, after working in ALEX, if you want to talk through anything at all related to this, definitely reach out and let me know. So this is also why chemists measure the numbers of atoms, molecules, ions, etc. in terms of moles. And why knowing the molar mass in this concept, that the molar mass is reported in grams per mole, is extremely important here. Here are our final answers reported in the correct number of sig figs. We're going to do a lot more examples with the use of Avogadro's number coming up. For example, we can also convert between mass and the number of atoms. To do this, we need the molar mass in grams per mole. We also need Avogadro's number. For example, if we start out with the mass of the element in grams, or lowercase m, we can go to the number of moles of the element, or lowercase n. From there, we can go to the number of atoms of an element, or uppercase n. So I have this example written out for you here. The work is written out here, but I want to show you this a little bit more clearly and explicitly. For example, let's say we have 1.66 times 10 to the negative 24th grams of carbon-12. Let's say we have that many grams of carbon-12 and we want to go into atoms. When I write out questions like this, I like to label everything really clearly. So at this point we have grams, but we want atoms. The first step in this is to go to the number of moles. How do we go from grams of carbon-12 into moles of carbon-12? Well, we need the atomic mass, the average atomic mass. So for carbon, about 12.01 grams per mole. Where did we get this? We look at the periodic table. So for carbon-12 to have this atomic mass, and we want to go into moles, we can orient this conversion factor then to be 12.01 grams per mole, or 1 mole over 12.01 grams. To be able to cancel out grams and be left with moles, we need to use this version. So 12.01 grams of carbon-12 in the denominator, 1 mole of carbon-12 in the numerator. At this point, we can cancel out grams of carbon-12, grams of carbon-12. We're left with just moles of carbon-12. Really importantly, what we just utilized is this big concept of the molar mass to go between grams and moles. Now our new starting point is this many moles of carbon-12. We want to get this moles into atoms. Here's this slide I included again, these different conversions using the mole. Here's how we go from atoms to moles, particles to moles, ions to moles, molecules to moles. Here, we're trying to go from atoms to moles. Or for our case, we want to go from moles into atoms, so we need to use this conversion factor and orient it in the correct way. So this is how we're going to end up using Avogadro's number for all sorts of styles of problems, all sorts of types of problems. So remember, we always put 6.022 times 10 to the 23rd atoms, particles, whatever it is, per 1 mole. So to orient this, then we would keep 6.022 times 10 to the 23rd atoms of carbon-12 in the numerator over 1 mole of carbon-12. That would allow us to cancel out moles of carbon-12 to leave us with just atoms of carbon-12. So when we do this calculation, we end up with 0.0832 atoms of carbon-12. The main gist I want you to take away from this example is how to go from grams into moles. So we use the atomic mass of carbon in grams per mole. Then once we're in moles, we can use Avogadro's number. And here we wanted to know the number of atoms specifically. So we filled in atoms here. 6.022 times 10 to the 23rd atoms per 1 mole. This helped us just get atoms in the end. So really what I want you to take away from here is to go from the mass in grams to the number of moles to the number of atoms. Here we use the molar mass in grams per mole. Here we use Avogadro's number. We're going to do more examples of this, so hopefully it becomes clear as we go on. What this slide is showing here is to go between mass and atoms again. The takeaway that's important for this slide is to be able to go from atoms back into mass. Here again, we're still going to use Avogadro's number. Here again, we're still going to use the molar mass. Let's do an example going from atoms back into mass. In fact, let's prove that this many atoms does weigh this tiny little mass for carbon. Also, I didn't point out that we can have 3 sig figs here. We have 3 sig figs in our starting value. So let's start with this many atoms. What do we want to do if we want to go from atoms to mass? Here we need to go from atoms to moles first, then we can go from moles to mass in grams. How do we go between atoms and moles? Again, we use this conversion factor oriented such that atoms is here per 1 mole. 6.022 times 10 to the 23rd atoms per 1 mole. So this many atoms per 1 mole, we can reorient it such that 1 mole per this many atoms. That's the same thing. So if we want to go from atoms to grams, we need to stop at moles. To do that, we need to use this form of this conversion factor so that atoms and atoms cancel out. So I'm orienting it like this, and I'm labeling everything. So atoms cancels out, we're left with just moles of carbon-12, still technically carbon-12 atoms. When we do this calculation, we should get 1.3816. We want to leave as many sig figs as we can until the end, times 10 to the negative 25th. What unit do we have? Just moles of carbon-12 atoms. Now, if we have moles and we want to get into grams, then we need the molar mass. The molar mass is how we go between grams and moles, because conveniently the units here are grams per mole. For carbon-12, this is 12 grams per mole. So to go between moles and grams, do we put moles on top or do we put grams on top? So 12 grams per 1 mole or 1 mole per 12 grams, same thing. So then we say 12 grams per 1 mole. For the units, moles would cancel out, leaving just grams. So that's how we can go between atoms to grams or grams to atoms. We need the molar mass, and we need to make use of Avogadro's number. So we're taking this long number multiplied by 12 to get just units of grams in the end. This comes out to 1.65792 times 10 to the negative 24th. If we round that to just 3 sig figs, 1.66 times 10 to the negative 24th. What's importantly our unit? It's just grams of carbon-12. Okay, so that is our final answer. Atoms to grams, grams back to atoms. Hopefully this is becoming more comfortable for you. This example that's been on these last 2 slides is showing 1 atomic mass unit and how many grams that really is. We know for carbon-12 that we have 12 atomic mass units, but this calculation shows the mass of just 1 atomic mass unit. So while not necessary, feel free to go through this equation and understand how we set all this up. Here's the important factor here, our use of Avogadro's number. Here's the other really important conversion factor here, using molar mass or grams per mole. These are the 2 main conversion factors you should start to be comfortable with at this point. Keep this slide handy. Know that you can substitute in pretty much any elementary entity, be it atoms, molecules, particles, ions, compounds, etc. So Avogadro's number of any elementary entity per 1 mole. We're going to do more practice with molar mass and with moles. I jumped ahead earlier to talking about water. So hetero meaning different. Diatomic, so meaning 2 different atoms. So we're going to talk about calculating and using the molar mass for more complex molecules or compounds, specifically ones that are composed of 2 different types of atoms. So we talked a ton about the molar mass so far. This is units of grams per mole of any item. Recall also this concept we've talked about before as well. The atomic mass is the mass of any atom in atomic mass units, or AMU. Very importantly, 1 atomic mass unit is the same thing as 1 gram per mole. So far we've talked about carbon, sodium, aluminum. These are all individual atoms, right? Well, as I showed you earlier for water, we can also get a molar mass for more complex compounds or molecules, not just for atoms. When we find the molar mass of a molecule or a compound, we call this its molecular mass. These are pretty much the same thing. Molecular mass is for molecules. It's still in units of grams per mole. So molecular mass or molecular weight, the weight of a molecule, it's the sum of the atomic masses in a molecule. We looked at water previously. We summed up the atomic mass of 2 hydrogens plus an oxygen to get the molecular mass of water as 18 grams per mole. So we can do this for carbon, sodium, aluminum, all sorts of types of atoms, as well as any molecular compound that is composed of these atoms. Let's go through another example now. So how about SO2? Well, is this a molecular compound or an ionic compound? Hopefully you identify that sulfur and oxygen are both non-metals, making this a molecular compound. If this is a molecular compound, we need to name this as the first element, then that prefix, and then we change the anion to end in IDE. If we're looking at sulfur dioxide and we want the molecular mass of sulfur dioxide, we need to look at the atoms that make up sulfur dioxide. That's 1 sulfur atom and 2 oxygen atoms. So to find the molecular mass of sulfur dioxide, or SO2, we need to go to the periodic table and find the atomic mass unit for sulfur and for oxygen. Then we add these together. There's 1 sulfur atom, there's 2 oxygen atoms, so 32.07 plus, in parentheses here, 2 times 16 for the oxygens, gives us this molecular mass of sulfur dioxide. 64.07 AMU is the same thing as 64.07 grams per mole. So 64.07 grams of sulfur dioxide is 1 mole of sulfur dioxide. So here's where we get this grams per mole. So we can do this for any molecule that's composed of any combination of atoms. For water, H2O, we know 16 is the mass of oxygen, hydrogen is 1. For sulfur dioxide, we find sulfur, we see that 32.066. Then we also needed the atomic mass of oxygen, or 16. So we're getting really comfortable with using the periodic table, identifying the atomic number, identifying the atomic mass. Let's do some more practice with molecular mass and Avogadro's number. So here in this problem, a chemist finds that 45.9 grams of magnesium oxide is produced. We want to know the number of moles of magnesium oxide that were produced. So we have the mass of a sample from lab. It's 45.9 grams of magnesium oxide. Is this ionic or is this molecular? Well, magnesium is a metal, so this is an example of an ionic compound. How do we know magnesium is a metal? Well, we find it here as an alkaline earth metal, group 2. One thing I want to make clear is that the mass of a sample, we can weigh out any number of grams of pretty much anything as long as it's small enough. We could weigh the mass of a car, it would be more difficult, but the distinction I want to make here is that this many grams, this does not tell us anything about the molar mass. So we just measured this many grams, but it doesn't mean anything about the molar mass of magnesium oxide. The molar mass or the molecular mass, right? So this is kind of an individual piece of data on its own. To solve this problem though, we do need the molar mass of magnesium oxide. We're going from grams, we want the number of moles, and to do so, we need the conversion factor of grams per mole. This molar mass or molecular mass never changes. For magnesium oxide, for example, it will always have the same molecular mass. We can weigh out various gram amounts of magnesium oxide, but again, the molar mass, the molecular mass of it, is always the same. How do we find the molecular mass? Well, we look at the periodic table. Magnesium has an atomic mass of 24.305 AMU. So 24.305 AMU, or the same thing as grams per mole. Oxygen, we've seen before, that's about 15.99 or 16 AMU or grams per mole. Again, we're kind of ignoring this mass for a second because we first need to figure out the molar mass. The molar mass is completely separate from however much amount that the person weighed out in lab. These are unrelated. We're going to use the molar mass to tell us how many moles were weighed out, but we need to find this first on its own. So to find the molecular mass of magnesium oxide, we take the mass of 1 magnesium and 1 oxygen. So we would end up adding these two together. When we add those two together, we get this many grams per mole. Remember, if something is raised to the power of -1, it's really the same as it's in the denominator. So this is the same thing as grams per mole. So grams times mole to the -1 is the same thing as grams per mole. Okay, so just a quick reminder on that. I've talked about this mostly, but let's go through these points to make sure. So here's the chemical formula. Each formula unit of magnesium oxide contains 1 atom of magnesium and 1 atom of oxygen. Now, what this also tells us is that each mole of magnesium oxide will contain 1 mole of magnesium and 1 mole of oxygen atoms. So 1 mole of magnesium atoms, 1 mole of oxygen atoms per 1 mole of magnesium oxide. To see this written out, 1 mole of magnesium atoms per 1 mole of magnesium oxide. How do we know that? It's because these subscripts here are 1. So because these subscripts are 1, we can make connections like this. So similarly, 1 mole of oxygen atoms per 1 mole of magnesium oxide. Well, what if those subscripts aren't always 1? Like here, this is 2. That means that 2 moles of hydrogen atoms are present per 1 mole of water. Notice importantly here, this subscript then tells us this number of moles here. Similarly then, 2 atoms of hydrogen per molecule of water. Okay, so these subscripts tell us a lot. We will do more practice with this. And so to figure out the molar mass or molecular mass of magnesium oxide, you notice that we're using those interchangeably. It's the molar mass of the magnesium plus the molar mass of oxygen. Okay, so we've covered this. Let's go back to answering our practice problem. So what we just figured out, what we just calculated, is the molar mass of magnesium oxide is 40.3044 grams of magnesium oxide per 1 mole of magnesium oxide. So we have this conversion factor, we have the molar mass. Now we can bring back in the specific amount of grams that were weighed out. I really recommend writing out each unit and what the unit is referring to every time, just to keep things clear. We have this conversion factor now, but we want to cancel out grams to answer this number of moles. That means we need to switch this conversion factor and flip it so we have grams in the denominator and moles up top to be able to cancel out grams. So we say mole of MgO per 40.3044 grams. When we orient it like this, grams of MgO, Again, I like to specify here, so those would cancel out, leaving just moles of MgO. When we do this division, we get 1.13883, but we only need 3 sig figs, so we end up rounding this to 1.14 moles of MgO, which we know how to name this now, of magnesium oxide. Let's go through this next topic now from 3A, so finding the molar mass from a chemical formula. Now we have a more complex molecule, so it has carbon, hydrogen, and oxygen. Here we're asked to calculate the molar mass or molecular mass of methanol. The chemical formula for methanol is CH3OH. So in finding the molar mass of this entire molecule, we need to look at the individual elements that make up that molecule. Then we look at the periodic table, we find the molar mass of each of these elements. Then we factor in that there are 4 hydrogens, 1 oxygen, 1 carbon, to then get the entire molar mass for the whole molecule. One thing that's important to do right away that will make it easier is we see we have 1 carbon. For hydrogens, we have 3 here and 1 here. Remember, that's an implied subscript of 1. In total, then, we have 4 hydrogen atoms. Next, for oxygen, we have 1 oxygen atom, so we can check that off. We have 1 oxygen atom in this molecule. This combination of atoms, these total up to make up 1 molecule of methanol. Right, so 1 carbon, 1 oxygen, and 4 hydrogen. So from this starting point then, we can go to our handy, very handy periodic table, and we find the molar masses for carbon, hydrogen, and oxygen. Carbon weighs about 12 grams per mole. There's only 1 carbon present, so that's to account for the 1 carbon atom in this molecule. Next, for hydrogen, it weighs about 1 atomic mass unit or gram per mole. There are 4 total, so we need to multiply this atomic mass by 4. That will account for all the hydrogen. Next, oxygen, we've seen this a few times. It's about 16 AMU or about 16 grams per mole. There's 1 present, so we would multiply 1 times 16 and then sum all of these together. Be sure to multiply this first. So there's 1 carbon atom, multiply that first. We'd also need to multiply 4 times the weight of 1 hydrogen atom. So multiply those first, then we add all them together. Therefore, for 1 molecule of methanol, we get a molar mass or molecular mass of 32.04 grams per mole. We were told in the problem to round to 2 decimal places, so we can do that. We use molar mass and molecular mass interchangeably. What would be the incorrect way to say this technically is that the atomic mass of methanol weighs 32.04 grams per mole. Why is that wrong? This is not 1 single atom, it's a molecule. So the molecular mass or the molar mass is fine, but we wouldn't say the atomic mass. We can say atomic mass for just carbon, hydrogen, oxygen, but again, this is more than just 1 single atom. This next topic, we've actually already gone through an example, but it's really important to get a lot of practice here. So here, interconverting the number of atoms and the mass of a compound. This should sound familiar. It's going to be good to get, again, a lot more practice on this. So here in this practice problem, calculate the mass of tetraborane that contains 1 trillion hydrogen atoms. Again, more practice in the main slide deck. What I want you to get comfortable with is the different combinations. So mass to moles, moles to mass, molecules to moles, moles to molecules, atoms to grams, grams to atoms. So all these different combinations you should start to get really comfortable with. Let's talk through this now, then we'll solve the problem. To go from moles to mass, where mass is often measured in grams, we need to use the molar mass. So we've seen that before, we're getting more comfortable with that. We need to be careful about what unit we have on top so we can cancel out either grams or moles depending on the problem. So we can go back from mass to moles, also using the molar mass. Here we're either multiplying by the molar mass or dividing by the molar mass. To go from moles to the number of molecules, atoms, etc., that's when we started to use Avogadro's number. These were on their own slide previously. Remember, we can go from atoms to moles, particles to moles, numbers of molecules to moles, numbers of ions to moles. To do this, we're going to use Avogadro's number. And again, we have to be careful to either have Avogadro's number in the numerator. We know we can switch these around too to have Avogadro's number in the denominator. What we'll also need here is that the subscripts in a chemical formula tells us the number of moles of that element per mole of the compound. Here we have a formula of B4H10. That means there are 10 moles of hydrogen per 1 mole of B4H10. We saw this for water. For 1 mole of water, that's 2 moles of hydrogen per 1 mole of water. It would be 1 mole of oxygen, also per 1 mole of water. Here we're working with an even more complex molecule, but that's okay. We know how to write this out. So we have 10 moles of hydrogen per 1 mole of B4H10. And then for boron, we can say we have 4 moles of boron per 1 mole of B4H10. Okay, so we can take these subscripts and then write out these different conversion factors. You may be wondering why we have 4 moles of boron per 1 mole of B4H10. How does that work? If this is our whole molecule, and in 1 mole of this molecule, we actually have 4 moles of boron. Well, coming back here for a second, we know that a mole of carbon looks pretty different than a mole of sulfur, looks pretty different than 1 mole of copper. So 1 mole of B4H10, that's consisting of 4 moles of just this element boron and just 10 moles of this element hydrogen. Okay, so another important connection to make with these subscripts to be able to write out these different conversion factors. So here we just address 10 moles of hydrogen per 1 mole of B4H10. This image is another representation of how we go from mass to moles to a number of atoms, particles, molecules, etc. We use the molar mass and we use Avogadro's number to go between mass ultimately to numbers of atoms, molecules, particles, ions, etc. We also know we can go the reverse direction. In this practice problem, to refresh ourselves, here we're starting with the number of hydrogen atoms. So we have atoms, but we ultimately want mass in grams. So if we have hydrogen atoms, the number, we have 1 trillion, but we want grams of a molecule. Well, one step we need to take is to go from atoms to moles. All right, so we have a number right now, but we want to go to moles in order to then get to a mass. We're working with hydrogen atoms, but we want moles, so we're going to use this version of the conversion factor. We want to cancel out atoms, but leave moles. So how do we orient that conversion factor? Well, it means we need 6.022 times 10 to the 23rd H atoms in the denominator per 1 mole of H atoms. When we stop here, these cancel out, H atoms and H atoms. Then we're left with moles of hydrogen atoms. That gives us 1.6606 times 10 to the negative 12th moles of hydrogen. Again, really important to label everything because we end up needing to use this conversion here because we want mass of the whole compound, not just mass of the hydrogen. So let's use this and let's use this to then go into moles of the whole compound. It won't be helpful to go from moles of hydrogen to grams of hydrogen because we don't have a connection between grams of B4H10 to grams of hydrogen. When making these style of conversions, we need to stay in moles because we have this mole ratio here. We don't know how many grams of B4H10 is the equivalent of grams of hydrogen. We don't know that. We do know that for every 10 moles of hydrogen, we have 1 mole of B4H10. If you're wondering why can't we go from grams of B4H10 to grams of hydrogen, well, we can. It just gets a whole lot more unnecessarily complicated. For instance, if we have grams of B4H10, we still need the molar mass, so grams per mole of B4H10, we cancel out grams. We still need this connection that for every 1 mole of B4H10, we have 10 moles of hydrogen. Then to finally connect this to from grams of B4H10 to grams of hydrogen, again, we'd have to go through all of these steps. Instead, when you want to go between B4H10 and hydrogen, we use this conversion factor here. We stay in moles. So moles will be our best friend for a lot of these conversion factors. When in doubt, convert to moles. Okay, so we're back here. We talked about this. We have moles of hydrogen. We don't want to go into grams of hydrogen, right? We want to stay in moles of hydrogen and then go to moles of B4H10. After we have moles of B4H10, then we can go to grams of B4H10. Okay, so we have this many moles of hydrogen. We need to use this conversion factor. We want to put moles of hydrogen in the denominator, so moles of hydrogen cancels out. There's 10 moles of hydrogen per every 1 mole of B4H10. If we were to stop here, moles of hydrogen cancels out with moles of hydrogen, then we're left with just moles of B4H10. For that answer, we're dividing by 10, so 1.6606 times 10 to the negative 13th moles of B4H10. So we have moles of the whole compound, but we're not quite done. We're asked for grams of the whole compound. So to go from moles of B4H10 into grams of B4H10, what is that magical conversion factor we need? It's the molecular mass. How do we find the molecular mass of B4H10? Let's do it. Let's calculate that. B4H10, there's 4 borons and 10 hydrogen atoms. Hydrogen we've used a few times, weighs about 1.008 grams per mole, or AMU. What about boron? So boron weighs 10.811 grams per mole. So now that we have the individual atomic masses of boron and hydrogen, we need to account for that there are 4 borons and 10 hydrogen atoms in this molecule. So 4 times this and 10 times this. Then we add them together. So for B4H10, we get 53.324 grams per mole, or atomic mass units. So in Alex, and again, depending on just a slight version of a difference in your periodic table, we got about this number. Let's go ahead and use a molar mass of 53.323. Just slight differences in the molar mass calculation won't make a difference in our final answer. So 53.323, this is grams per mole. We know we can also rewrite that as 1 mole over 53.323 grams. If we have moles here and we want grams, which version do we need to use? So this one will allow us to cancel moles and keep grams on top. So 53.323 grams per 1 mole of B4H10. Moles will cancel out, moles will cancel out. We're left with just grams. Really importantly, we're left with grams of B4H10, not just grams of hydrogen. With moles of B4H10, then we can use its molar mass to get just grams of B4H10. Doing this multiplication, we'll get 8.8546 times 10 to the negative 12 grams. We were told to round to 3 sig figs, so we can do that. 8.854 keeps the 5 as a 5, so 8.85 times 10 to the negative 12 grams. In addition to doing these calculations, it's also important to recognize what this value is telling us. This is a really, really small mass, times 10 to the negative 12 grams. So we took a trillion hydrogen atoms. And turns out with a trillion hydrogen atoms, we still only have this still extremely small mass of B4H10. So if there are a trillion atoms present in the form of this molecule, that still only weighs 8.85 times 10 to the negative 12 grams. So atoms are extremely small. So we're at the end of part 1 for chapter 3A. I again want to point out the more practice problems in the main slide deck. So be sure to look through those, practice in Alex, reach out to me in office hours, and I'll talk to you next time for chapter 3A part 2.